All right, so my name's Tovio Roberts, and this is another episode, if we can call them that, of latent topics in data science. And we're going to be looking at prime numbers and windows of prime numbers. So there's an associated GitHub repo for this, and I'm going to do my best to keep it reasonably current as I'm coding things out. Sometimes I forget to sync things up, but yeah, I'll do my best. And I'm putting that link in a few places. I'm putting in the chat right now. And that's what you're seeing in this window right here, exploring prime windows. And what we're going to do here essentially is look at, let's say, from 0 to 10,000, the prime numbers in that range. And then we're going to kind of break it down and look at the distances between the prime numbers and build a distribution of distances where we can then sort of make a visual comparison between 0 to 10,000, and then 10,000 to 20,000, then 20,000 to 30,000. And this will be a little bit heavy on the visualization, but given that we have enough time, I'll probably dump down a data set as well, because I think there's a lot we could do with this data set. I think it's kind of fun. So I've been playing around with this all morning and kind of getting it into a place where there's something to show. And so I'm going to code up to what I have, and then I'm going to go further than that. And this is all going to start off pretty simple. So here's the repo. I'm just going to clone it down. I'm going to grab this URL right here and just clone it. And I'm going to go in there, exploring prime windows. Let's see. Oh, I see. I almost never use dashes, and for some reason I did this time. So notice there's nothing in here yet, and I'm just going to start a session of VS Code. And VS Code's going to throw a bunch of pop-ups in my face because somebody thought that's a good idea. Maybe not a bunch of pop-ups, maybe just a couple. And yeah, all right. So this is our environment. I'm gonna, for the sake of just convenience, I'm going to code almost entirely in one Python file. So let's just make that Python file really quick. If I can resize my terminal. All right. So Python, actually, to call this exploring prime windows.py. And having done that, we've got that file here. And yeah, kind of the first thing that we can think about is, what is primeness, right? Simple enough. We're not going to accept any number as prime if it's divisible by some number that's greater than 1. And we can write an isPrime function pretty easily, and in a kind of, I don't know, a little bit of a brute force way. So let's do that. So isPrime of some number, and I'm going to go ahead and mute my Slack notifications really quick. just so that those aren't popping up while I'm coding. Okay. All right. So yeah, we're going to code out is prime. And I'm going to try to keep the level of coding here pretty accessible. There's going to be a couple things that I use that are, tools from other places that, if you're in the Galvanize data science prep materials, we don't introduce these tools, but, they're not all necessary for what I'm going to do here. There are certain times where, let's say there's a more appropriate data structure to use in Python. I'm not going to use that because it's not part of the sort of core language, so to speak. And I'm going to do things with for loops when, there's faster ways to do some of these things. But I'm just saying that to qualify this code. And to, if you see something that you think could work better, take this code and make it better, Okay, so is prime of some number. I'm going to write this in a fairly optimized way, but first I'm going to write it a little bit poorly. So not poorly. I'm going to write it just generically. So I'm going to say for, let's see, n in range, and let's go from 2 to the number. And this is not inclusive, right? So we're going to check for every one of these if the number is evenly divisible by 2, then we're going to return false. And if all of this runs, we can return true. And let's see if this works. So I'm going to say for num in range, and let's just go up to 100. Let's print the, let's see if we can just print the primes here. So if is prime of that number, then let's print the number. And over here, I'll just run Python. And let's look at this really quick. There's some obviously, there are some numbers in here that are not prime that we can see. 93 is not prime, that's divisible by 3. What else? 0, 1, right? These are not, these are undefined as prime numbers, so I'm going to go ahead and count for those by and we can see why this is doing this, right? Because there's no condition here that's going to prevent those. So I'm just going to, well, I'll fix it in the original function. Why not? So I'm going to say if the number is equal to 2 or the number is equal to 3, well, we know those are prime, and we're going to return true. And then we're going to ask another question if the number modulo 2 is, if the number is evenly divisible by 2 or the number is less than 2, right? We're not considering negative numbers in any, to have any kind of primeness here, and we're going to return false. So that's going to count for some things. It's not going to count for everything. And let's just take a look. We're still getting this divisible by 99. We're still getting this divisible by 93, or 99 is divisible by 3, 93 is divisible by 3. So let's make this a little better. So we're going to start at 3, and we're only going to go up to the square root of the number, which I'm going to represent as num to the 1/2, right? And we'll go one more than that. And we're going to go in 2s because there's no point in checking for an even number, right? Those are all divisible by 2. We know that. We've already ruled out certain types of divisibility. And we can say if, oh, there we go. That's why I have that 99, of course. Okay, if num modulo n is 0, we're going to return false. Otherwise, we're going to return true. So this is actually a fairly optimized function in its present form. And we're going to want an optimized function, or a somewhat optimized function, because we're going to be looking at kind of massive ranges of numbers. And this list of numbers over here, this is looking prime to me. I don't see any non-prime numbers in there. So this function is working. You know, basically we're throwing out 2 as an option, and we're incrementing our for loop by 2 up, you know, from 3 up until 1 more than the square root of this number, which we then cast as an int to make it able to create an iterable using the range function. So that should be pretty straightforward. And I'll go ahead and sync that. So I'm not going to write out proper commits for GitHub. I have a little bash function called git-adder, which is a Letterkenny reference, but that doesn't really matter. Git-adder, and then I'm just going to say add is prime function, and that should sync up. And so if we look over at GitHub, these files should, or that file should be here. If I look at exploringprimewindows.py, then that's there. So if you want to follow along with the code, that should all be there. And cool. Let's continue forward. So we're going to think about this. We're going to think about distances between prime numbers. And to do that, we're going to write another function that is, it's one of these kinds of classic functions that you might learn or do in a challenge somewhere. You might do it on Code Wars. So we're going to, given a number, like given the number 7, what is the next prime from 7? Well, it's 11, right? So we're going to write a function that's going to get that for us. So I'm going to do this with a while loop. If you know me in coding Python, I very rarely use while loops in Python, but I'm going to do it here. So I'm going to start with a count, say just this number plus 1, right? So the first thing we're checking is the next number from the argument that's passed in. And I'm going to just make a quick Boolean flag. And this will allow us an exit condition from our while loop. And an interesting thing about this, we could probably use a for loop here. And instead of using a while, we could say for some number in range and, you know, have a max there of some distance between 2 prime numbers, right? Like 120 or something like that. I'm not sure about this, but I think in all the numbers between 0 and 1,000,000, I don't think you ever go more than 120 between primes. I might be wrong about that. When we're done with this today, we can actually check to see if that's true. But even if I did a number like 500, we can't guarantee that this is going to work for an arbitrary window of an arbitrary window of numbers, right? Like, what if we're up in the trillions and looking at a window of 10,000 numbers in the trillions? Well, then, you know, unless we're using a for loop and assuming we're never going to look at a window greater than 10,000, well, then we could do for, you know, I in range 10,000. We could do something like that to replace our while loop. But that said, I'm just going to use a while loop in this case, even though I tend to avoid them. So while looking equals true, obviously I don't need to do that because this is just a while true at the moment. I'm going to say if is prime of the count, right? Then let's do continue looking, and we'll just set that to false. So we're setting the flag, and we're breaking, and we're going to increment this count. So I think that's pretty straightforward. This function I'm not so worried about optimizing. Let's just throw in some numbers here. So print, let's find the next prime of 7. And run this over here. It's 11. What's the next prime from 11? It's 13. From 13, we're going to go up a little bit more. Going to go to 17. And we can start thinking of these distances at this point. But this is only performing the action of finding the next prime. So I'll go ahead and sync this. Okay. And all right. So the next thing we're going to think about is building a window of primes. And this is just going to be all the primes within some range of integers, from some low value to a high value. And this is pretty straightforward, right? We can just say, let's get the primes in a window. And I don't know if this is a technical term, prime windows. It just seems like it's a window, right, of numbers. And so that's what I've been calling it. When I started thinking about this problem, I made a point to not read anything about primes or what might be called prime windows or distances between primes. I kind of, I'm going to, after this, I'm going to go read up on primes a little bit more and see what kind of research there is around kind of this topic, because I'm sure somebody's done it. But that's part of the idea here is that I am taking something I don't know much about, and I'm using Python to explore it. And you know, I'm thinking about it, I'm visualizing it, and I'm building a data set, and from that data set I can do more. And I could just go read about it, and probably reading about it would answer a lot of my questions and bring up more questions, but I'm becoming familiar with these concepts through just, you know, writing some code. So I'm thinking about these prime windows, and this is going to go from a low value to a high value. And you can imagine this as being, if the window is 10,000, then it's going from 0 to 10,000. And we're going to be exclusive of the high value in this. So I'm going to just do, I'm going to do a comprehension here. And, well, you know what? I'll go ahead and write it as a for loop first, and then I'll turn it into a comprehension. So I'll say, I'll just make a list called primes. I'm going to say for num in range from low val to high val. If is prime of that num, then I'm going to append it, primes.append, and I'm going to append the num, and then I'm going to return the primes. So let's take a look at this and see if it's doing what we'd expect it to do. And let's go from 0 to 10,000. And I'm not printing anything, so let me print those numbers. That's not very readable, so maybe I'll just actually for num in that, and I'll print the num. So here's all the primes. This is just a list of primes between 0 and 10,000. Really straightforward. I'm going to rewrite this function. Well, first I'll commit the code here. And let's see, right, get primes for loop. And I'm just going to rewrite this because this is a perfect situation for using a comprehension. Comprehensions will be much faster for these kinds of operations. So I'm going to say num for num in range, and I'm going to go from the low val to the high val. And if is prime of that number is true. I don't actually need to say double equals true here, but you know, sometimes I like, you know, for educational stuff, I like being really explicit about this, even though it's a little less Pythonic. So if I run this again, we should see the same thing. And we do. So that's pretty straightforward. And I'll go ahead and sync this up with comprehension. Okay. So we are getting primes in a window. And now we're going to kind of move forward because, you know, thinking about, maybe I'll just I'll demonstrate this. I'll just run this twice. Let's say here, and I'll print this as it is. If we're thinking about, oh, probably need to put values in there. Okay. If we're thinking about the distances between these numbers, right? So we're starting, well, let's look up here. So the distance between 9973 and 9967. Our interest here is to build a distribution of distances. And that distance kind of, you know, that looks, what is that? That's 6. This is a distance of 6. And, you know, this is a distance of 18, right? And we're going to build a list of distances. And this is interesting in some sense because it's not going to be a parallel list to what we're seeing here. It's not going to be parallel to the list of primes. It's going to be one less, right? Because we're looking at the spaces in between what we have here. So we're going to take this list and we're going to put that into another function called getDistances, and we're going to return the distances between the prime numbers for a given window of primes. So let's call this getDistances, and we're going to pass in a list of primes. I'm going to call it primes list, and I'm going to take that primes list and I'm going to reverse it. And you'll see, hopefully you'll see why in just a moment. So here's kind of the best way, well, arguably the best way to reverse a list. This is syntactically a really nice way to do it. I could do list of reverse of primes list. I don't want to just do primes list dot reverse because by convention or prime list, by convention, well, maybe I'll just name this primes list. I think that's a better name. By convention, you don't want to modify the parameter. So, you know, I could have done something like primes gets primes list dot copy and then primes dot reverse to do an in-place reversal. But all this is to say, I'm not going to do that. I'm going to do it this way. It's easy. And then I have this rev, which just short for reverse. This is my this is my reversed primes list. So I'm making this variable temporarily. And I'm going to, consider my output or my result. Maybe I'll just call this output. My output here, which is going to be my distances. Let's name it what it is. This is going to, I'm going to take all of these reversed values and except for the first one. So starting with the highest number, I'm basically making something like an offset, if that makes sense. So I'm excluding this one so that I have near parallelism in reverse, but the same index that points to this last number in rev is going to point to this second to last number in distances. And that's just going to make subtraction easy. And to do that subtraction, I'm actually going to use a comprehension here because I find this to be the easiest way for myself to understand it. I'm going to take the number minus minus the, you know what? Distances is not a great thing here. Let's call this the offset. So num minus the offset. And I'm going to index this one. So I'm going to access this one and index this one. So if you're familiar, I'm using enumerate here for the index and number in enumeration of the reversed list. And I'm going to go from the 0th index all the way up until 1 minus the length of this. That way I don't get an index out of bounds error. And let's see. Sometimes it's hard to see where these, okay, so that, I think I see what's going on here. So length of rev minus 1. I think I want to do that. And then, okay. So this is going to return the distances, but in reversed order, actually. So what I'm going to do is just reverse it again. And that's what that looks like. So I'm taking each number in rev and each number, so this is each number in rev, this is each number in offset, and then I'm just subtracting them, and that's how I'm getting the distance. And this number in rev should always be greater than this number in offset, and so I don't have to worry about accounting for negatives or anything here in this kind of distance calculation. And then I'm only indexing up until, instead of length of rev here, I could have done length of offset, because offset should be 1 less than rev. But I think this is, well, this, in some ways, if there's something wrong here, I'll find it because of this, right? If the distance is too different, then this should throw an error, index out of bounds error. And then I'm just taking that result and reversing it so that we can see the distances in the, from lowest to highest. So all that, and let's just run it. So I'm going to grab this. So I need to get a primes list from somewhere. To get that primes list, I'm going to just run this function, the get primes in window, and we're going to go again from 0 to 10,000. And there's probably an error somewhere, and we'll find out in a sec. There is definitely an error because there's no such thing as enumeration. Well, no such function as enumeration. There's a function called enumerate. Okay, int object is not subscriptable. Interesting. Okay, so probably have some kind of line 36, of course. Okay. So return num minus result sub idx offset sub idx for idx common num enumerate verse length rev minus 1 Huh. I am not seeing the error here. If someone watching is seeing this error, if you want to like let me know what it is, this is the kind of thing that it's always nice to have second eyes on. Okay, let me just look at this error a little bit more. In get distances, return num minus offset idx for idx num in enumerate rev. Okay. Get primes window. All right. Yeah, this is the joy of live coding, right? Is finding the error. All right, num minus offset sub idx for idx. Int object is not subscriptable. I wonder if IPython will give me a better message here. Let's see. Oh, offset. Okay. Same error. I don't know, Clark. I think you're around. Do you see what my error is here? Sometimes you need to phone a friend. So I'm going to Slack Clark Walker my code really quick and see what he has to say about it. Okay. All right, so I guess I'm gonna kind of walk through this again and see what I'm missing. Oh my gosh. Okay. I think that's it. All right. Okay. I was missing a colon right here. So yeah, that isn't going to do anything. That's what I need to do. So I was basically setting offset to be the second value in rev as opposed to everything from the second value on. So mystery solved. Whew, okay. Let's go from there. All right, so we can see over here that we're getting the distances. And it might be nice to look at this in context of, okay, well, we've got, this should be between 2 and 3, right? 2 and 3 is 1, between 3 and 5 is 2, between 5 and 7 is 2, between 7 and 11 is 4, between 11 and 13 is 2, between 13 and 17 is 4, 17 and 19 is 2. This looks like it's working, you know, and we could do some random testing, but we're gonna just say that it's probably doing all right. And maybe I'll leave, I'm gonna get out of IPython for reasons that I'm not going to say quite yet. All right, so I'll comment this out. And, you know, notice that there's this stack of functions right here. I'm gonna go ahead and do something I like to do and separate my functions from my my procedural code. And that's just gonna look like this with this if main block. So let's just get attr somewhere up here. Okay, I'll just type it from scratch, get attr and add get distances function. I'm naming these with a get syntax, and if you're from another language, you're probably familiar with setters and getters. And Python tends to discourage getters for classes, but I find this naming convention to just say what it's doing. And if I was to rewrite this into a class, I would probably get rid of the get in here because it would be misleading to somebody reading my code. I would just call it distances. But for what we're doing here, I think it's semantically kind of nice. That's an opinion. I'm not gonna stick to that opinion if somebody has a better opinion. So we can get distances now between primes. So we can get the distances, and if you're in any of our prep classes, you probably have seen this dictionary paradigm. And I'm going to write a function that is going to build us a representation of the distribution of distances between prime numbers within a window of primes. So let's call this build primes distance distribution. And we're going to pass in a primes distance window. And there's a couple ways I'm going to do this, and it's not going to seem entirely obvious why yet. So I'm going to just include 0 counts in this. I'm going to say include zeros is true. So there are distances. If we, and I'll just, you know, this is going to return a list. This get distances of get distances of get primes in window. I'm going to just, oh, okay, there it is. All right. So we have this list of distances, and notice that there's no odd numbers in here, right? Except for 1, and that's because, and this is the only window that will have an odd number in it, the number 1. Anything starting with a low value greater than 1 will not have any odd numbers in it. And that kind of makes sense, right? Because if you add an odd number to an odd number, all primes, except for 2, are odd. If you add an odd number to an odd number, you get an even number. So we're not going to see any odd distances. And so it's a little nonsensical, maybe. It might be a little nonsensical to include 0 counted things, right? Like if I do .count here of 3, right? We shouldn't see, we should get, oops. What is happening there? Get distances. Oh, I didn't save it. Cool. Okay, we get 0 3s. There are no 3 distances in this, and that might be obvious, but I want to have an option to include the 0 counts, and I want that because later we're going to make a data set, and that data set, in order to make things that are comparable, it's just really helpful to have zeros. So I'm going to write this in 2 different ways within the same function. I'm going to make a dictionary, and I'm going to say if include zeros is true, then we're going to just go through a range for I in range, and we're going to go to the max of the primes in the primes distance window. And from this, we're going to say that for each of these numbers, right, for each number within that range, oh, this should probably be +1. Yeah, for every number in that range, we're going to say, we're going to just count the numbers, the number of occurrences of that value. And if I return the dictionary now, and I call this, and I'll just do that, I'll comment this out, and I'll say, let's print the result of this. Well, let's do this like we do any dictionary for key value in that dot items. We're going to just print, and we'll do K and V on here, and we'll just say for the primes distribution window, we'll borrow this, and so this should, well, we'll find out. There might be an error in here, but let's find out. Okay, cool. So, oh, I see. There's something. Ah, yeah, no, this works. This works. No, there is something wrong here. We shouldn't have quite this many distances. All right, if include zeros is true, for I in range, max of primes distance window +1. Oh, not get primes in window, get distances, right? Because we want to get the distances, and this is getting the primes. So that is not entirely helpful. Let's do build primes. Let's see. All right, so this should be all of this. I know it's a big mess right there, right? But we'll just have a quick see if this is working the way we expect it to. So Python exploring. Okay, so this is reasonable. There are no zeros, right? That wouldn't really make sense. There's one distance of 1, that's between 1 and 2. There's a distance of 205. There's some run of numbers in the 0 to 10,000 window that has distance of 205. But notice every odd number after 1 here is set to 0. And I'm doing this because if we consider this to be a vector, we can take 2 different windows, and even though they may have different lengths, because as we'll see, this distance, this max distance is going to grow. But even though 2 windows have different lengths, we can get a sense of their orientation to each other through cosine similarity. We're probably not going to get into that in today's kind of code through of this, but what we will do is plot a lot of this stuff, and we'll plot this with the zeros and we'll plot it without the zeros. So that's that function with zeros. And let's just write an else here and say, well, for distance in the primes distance window, if the distance is not in the dictionary already, then we'll just we'll put in a count of that distance. So this is going to give us a different result. And let's see, build primes distance distribution. I'm going to explicitly set include zeros to false. And we can just take a look at that. And this is way friendlier, right? This is it's a shorter space. We can kind of see where the top of this curve is, right? And I want you to just notice this number 6. And I don't know why this is. Maybe somebody has a lens into this. I don't know why 6 is sort of this transcendent number in prime windows. And I'm sure this, is, maybe there are windows where 6 is exceeded by a different number. A length 10,000 window where 6 is exceeded by a different number, but I haven't found it yet. And we'll just kind of take a look at that. We're probably not going to, go way, way high in the primes. We're probably just going to go up to, 1 million or 10 million or something. And but through all of that so far, what I've seen is that 6 is the most common distance between two prime numbers for whatever reason. And let's see. I will go ahead and write build primes distance distribution function. And there we are. Cool. Okay. What does the if name equals main block mean? Yeah, let me talk about that for a sec. This is nice. Well, I think it's nice. This just gives a good separation. For our purposes here, it's going to give a good separation between the functions that are written and the procedural code that's run. And that's not to say that you have to do this, because if I just delete this and move all of this back, well, it'll be fine. But one reason you do this is that if you write another Python file and you import functions from this, you might want this file to be runnable in and of itself. And in that case, having some procedural code that you can run is really helpful. This is really good for things like for terminal scripts, where you feed in some arguments, right? You run your Python script in your bash shell or in your shell, and you put in some arguments, and those get processed in here, and functions get called from up here. And you see this come really in handy when you're in object-oriented programming, writing classes and whatnot. So that's kind of a brief statement about this. Another way people do this, and this is how I usually do it, honestly, is I do an if name equals main, then run the main function, which I would define up here. This is this looks very Java-ish. If you've written in Java, it looks kind of like C, to have a main function, and then all your procedural code, or your global, not your globals necessarily, but you could put something like globals in there, but all your procedural code goes here. And this is if you run this file by itself and you're not calling it from somewhere else. But it's just a good practice. It gives you a nice separation between, you know, the functions that you're writing and the things that aren't functions. Like this is just a demonstration of the function. Yeah. Okay. So we are getting a distribution, and let's just take another peek at that just to, you know, make sure. Okay. Include zeros as false. Items. What am I missing? Oh. Weird. KV and build primes. Get primes in window, low val to high val. Include zeros as false. Unexpected indent. Okay. I think that was just an indentation error. Nope. Oh. Wonder if that's it. No. Okay. Oh. Yeah, okay. All right. This should be fine now. I was calling out to a main function that didn't exist, and it was telling me it was an indent error, which it probably was in some way. Okay, so there's our distribution, and these are just our counts of distances between primes. And so already you can see there are some very common ones in, there are some that are more common than others, right? And, you know, we can start asking questions, you know, how does this change as the windows move across, you know, a range of numbers, right? So if we were to get every window between 0 and 1,000,000, what would this look like? And to do that, we're going to start, well, we're going to plot these, and we're going to actually just take a look at what this is. So to plot this, I'm going to use matplotlib, and I'm going to do this import matplotlib.pyplot as plt. Plt is going to be just the alias, so I don't have to type this kind of thing over and over again. And I'm going to write a plotting function. And with the plotting function, you know, if you're not used to plotting, I'm going to write this, and then I'm going to push it up really quick so that you can start playing around with this, you know, sooner. It's the kind of thing where once you write a lot of plotting functions, I'd like to say that it always gets easier. It does, but it takes a while. And I'm sort of interested in getting to the visualization, so I'm probably going to sort of careen through this. So this is just the plotting of a single primes window. So I'm going to say we're going to pass in a distances distribution, which is the thing we just made, and we're going to go from the low of the window to the high of the window, and we're going to pass in a count of the primes. And I'm going to throw in something here that we'll see later. Basically, we're going to be making a lot of plots, and we're going to stitch them into a video. And this is saying that by default, we don't want the last plot to persist into the current plot. And this is just, we'll see it when we see it. And and it'll make more sense then. So I'm going to give us a message here, you know, where we know which window we're plotting, and we can kind of see in the terminal our progress. So, you know, if I'm thinking about this in terms of if we're calling this every time, many times, then I want to be able to see where we're at in terms of, you know, what plot we're on. Okay, so we need two things here. We need the distances and the counts. And I'm going to build these in a way where hopefully we can see what's happening, you know. There are sort of more compact ways to do this, but I'm going to do it in a longer hand. So I'm going to say for the key and the value in the sorted version of this distances distribution. So this is what we're getting out of here, right? This build primes distances distribution. That's what we're passing in. I'm going to take the sorted version of that, and the distances, I'm going to append the keys, and the counts, I'm going to append the values, and maybe just to be more explicit, I'll do this. So distances dot append, and we'll append the distance, and counts dot append, we'll append the count. Okay. And that's going to get us pretty far. So I think what I'll do is just get us some output really quick so we can see what these things look like. So I'm going to plot a scatter plot, and I'm also going to plot these same things, but in sort of a line plot. So I think that's all I need. And let's find out. So I'm going to grab all of this, and I'll go down here, and we need a distances distribution. So maybe what I'll do is take this and this. Oh, I don't need that. I'm going to take all of this, I'm going to put it into a dictionary, and I think get rid of that. So get rid of that dot items. Okay, so now we've got this dictionary. I'm going to pass that in, and I need to think about what the I need to think about what our window low is, right? And I can get that pretty easily. It's going to be where we start, and window high is going to be where we stop. So maybe what I'll do is start breaking this out, and I'll say window low is going to get 0, and window high is going to get 10,000. And then I'm going to have a window size. Oops. And actually, I'll come back to that. I'll just have a window size. So window low is going to be this. Window high is going to be, it's going to be window low plus the window size. And the primes count is going to be the length of these windows. So I'm going to just go ahead and break this out. Like so. And I'm going to just say primes list. And I'm going to get the, actually, I'll call this num primes. and I'll just get the length of this. Oh, no, I'm going to need it. Okay, so we'll pass in the primes list here, and we'll get the number of primes as the length of the primes list. And so we've got window low, we've got window high, we've got a primes count of the number of primes, and something is amiss. So what is wrong here? Well, let's find out. Okay. Name plot primes window is not defined. Def plot primes window. Oh, okay. No wonder it is not defined. It is on the wrong tab level. So let's see if that works. Cool. Okay. So, yeah. So this is what that first window of primes looks like. The first 10,000 length window looks like. And this is 6 right here. Assuming 2, 4, 6, 8, 10, 12, 14, 16. And yeah, this just gives us a sense of the shape of this. Now, it's a little misleading, and you know, I can make it it's misleading because there aren't values in between these little plateaus. And I think it's sort of a visualization convenience to have those lines. And if we don't have those lines and we go back to 0, it's going to, well, let's see if this, yeah, it's going to look like this. And so this is sort of another valid take, right? This is another valid visualization for the same thing. And I'm not sure which I prefer. I think they're both helpful, depending on, you know, what we're trying to think about here. So that's some very basics for this plot primes. I'm going to push this up, and then I'm going to extend the plot primes window function, because we're going to use it in some other ways. So yeah, let's extend this out. Okay, so I'm going to, let me think about the next thing to work on with this. I'm just going to put in some basic things that you should always have in a plot. I'm going to put in a title. This is sort of a superior title, and this is going to be the prime window between the low and the high. So we can see this in a second. I'm going to go from window low and go through window high. And after that, well, we have some information that we can use. So we've got the total number of primes. Why don't we just include that in a, there's subtitle, which is the title above, right? And then there's title, which is the title below a subtitle. So total primes, let's call this is going to be the primes count, which is up here. And let's think about the max distance. This is one of those things that, let's see, we've got distances. We can just grab this, and it's one of those things that I think is telling about a prime window. You know, in my very rudimentary understanding of primes, I think it's going to give us some insight into these prime windows. And we should have labels. We should have an X label and that is our distance. And we should have a y label, and that should be the occurrence of the distance in a given window. And yeah, so that should make things look a little nicer. And I'll just run this. We can take a look. Okay, so there's something wrong here. Total primes, this should be the length of the primes. Huh. I must be passing in down here. I'm passing in a primes list. I should be passing in the length of the primes list. Okay, that's what's going on there. And let's find where that is. Because I start typing the length. Okay, so that should make this look a little nicer. Okay, yeah. So between 0 and 10,000, there's, 1,229 total primes, and the maximum distance between any of those primes is 36. So that's already some data, right? That's some information that we can think about, and we could do something like, I could change the low here. I could set this to, 10,000. And we could take a look at the next window. And notice, again, this 6 is just transcendent. This is like nearly 300, right? So that's just something to see. And the maximum distance here, again, is 36. It's, this does not look that different from the first one, which is kind of cool. So let me continue with this plotting primes window function. So I want to put in a table of the most common primes. That's one of the things I'm going to do here. And to do that, I'm going to go up here to distances and counts. Actually, I'm going to go above this plotting here, and I'm going to say, I'm going to make I'm going to make a couple parallel lists. And it's going to be the sorted counts and the sorted distances. And I'm going to go ahead and go through the sorted zipped counts and distances. And I'm going to reverse on this sorted. And notice that what I've done here is I've swapped the counts and distances. So now the sorted counts are, the counts are going to be what's sorted here. So whatever has the highest count, because of this reverse equals true, whatever has the highest count is going to be the first value, or the first count in sorted counts, and whatever has the distance affiliated with that count is going to be parallelized in sorted distances. So this is a convenient way of maintaining parallelism. If you have parallel lists like this, this is a way you can maintain that parallelism while also transforming your data in a way that's going to be useful for plotting. And now I've got, so I'm putting my scatter plot here, and now I've got data that I can put in a table. And I think the table is helpful here, and we're going to use it as kind of a basis for looking at how certain things switch around. Let's see. Just checking to see if anybody has put any questions. Ooh, let me close that. All right, cool. So let's add in this table. Okay. So I'm going to just do this in a loop. I think it's easier to see it that way. For the distance and the count, going to zip the distances. Is this how I want to do this? No, I'll do this a different way. I'm going to say there are column labels, and I'm going to set these to a distance and a count. And these are just going to be the labels on the table. And then I'm going to just make a quick accumulator, and this will be all the table values. And I'll just say for I in range, and I want to do the top 15 because this table, I don't want it to extend. I really don't want it to extend forever. So I'm going to say for I in range 15, that's going to get us our 15 most common distances. I'm going to append the sorted distances up here, right? And append the sorted distances one by one, and I'm going to append the sorted counts one by one. So notice this is a sublist, or this is a sublist in the table vals. So this is going to be a bunch of length 2 lists. There's going to be 15 of them, and that's going to be our table. So we've got our table data, and now I'm going to go ahead and build the table. So I'm going to plt, right? plt.table. This is just plotting the table, and there's some text for the table, which is these table vals. And then I'm just going to set kind of an arbitrary column width here, and I think that'll look okay. That should look fine. Yeah, let's go with that. And we have these labels up here, these column labels, and I'm just going to set this to that, to the column labels, and I'm going to put this in a certain location. It's going to be in the center and to the right. And let's run that. Let's see how it goes. Cool. Okay. So we can see here that here's our distance. Our most common distance is 6 in this range. And the next most common is 2, and then 4, and then 10, and 12. And so what you're going to see, at least for all the windows I've looked at, is there's a distance, a most common distance of 6, and these numbers sort of swap around depending on the window, which is kind of cool. And let's make this a little nicer. So I'll go ahead and add that. So that should be synced up. And let's actually annotate this plot, because, you know, we're looking at this, and if we have this visualization, it might be nice to actually see a number on the tops of these. That's actually why I made these little pedestals, because I wanted to put a number on top of them. So I'm going to go ahead and do that. Let me think about this for a second. So we've got this here, and we need to have, yeah, so we need to be plotting there. And okay, this is the way I think this will work. Okay, so for the distance and the count in well, we've got these distances and counts. So I'm just gonna zip them. I'm going to make a label for each of those. And this label is going to be the distance, right? So the distance is just gonna sit on top of each of those little platforms. And there's a function called annotate. And I'm going to annotate these one by one. So this first thing, this label, this is passed in here. I'm building the label and then I'm passing it in here. So that's going to be what's actually rendered. And then I'm going to put the distance and the count in as my XY values, essentially. So this is where this is in the scatter plot. And then this is, I think this is the default, but I'm not sure on that. This offset points. And this allows me to offset the number by a certain amount. That said, I don't actually want to offset it. I want it to sit basically on those little platforms. So I'm going to give it a 0, 0 offset. And the horizontal alignment is going to be centered because I want it right above it. And I'm going to set the color to black. And I'm going to draw a little circle around each one. So this is a bounding box, and I'm just going to pass in some parameters here. So there's different types of bounding boxes, and I'm going to use a circle, which for our purposes here is a bounding box, and I'm going to give it a tiny bit of padding, just so the circle goes a little bit outside the number. And I'm going to make the color, that background color, yellow. And I'm going to make it a little transparent. So an alpha layer, if you're not familiar, is a transparency layer. So I think that looks good. Let's see. Ha. Okay. So that seems to be doing okay. And notice that we're annotating these odd numbers as well. Is there a good reason to annotate those? Probably not, right? But we can see, this kind of like this sort of stack of primes, like how this looks. It's kind of nice. And probably what's more beneficial here is including zeros, setting that to false, and running this again. And there we have our primes in our prime distances in relation to each other, which is, a big, we can do that. We can see these patterns. So I think that's the majority. Is that all I wanted to do with the plotting? No, there's a little bit more I want to do with it. Yeah. So I'm gonna put some limits on here. I'm gonna put a Y limit and an X limit. And the reason I'm doing this is we're gonna make a video of, oh, you know what? Let me go ahead and let me sync this with GitHub. We're gonna make a video, and we want the scale of the X and Y axis to be constant in that video. So I'm gonna put a Y max at 200, and remember this is the counts. So in those first couple plots, we actually exceed 200. Like 6 occurs, I think, 299 times on the second plot. But in this vast range, or in most of these windows, I think it's under 200. And that's not to guarantee that it's always under 200, but I think we can safely do 200 and you know, the first couple windows will not reflect, you know, it'll just be off the screen. And I think that's fine. So for the x-axis, this should, you know, we want to try to include the highest numbers, but we don't want our plot to squash down at all either. So, you know, in general, we're not seeing many distances over 100. And, you know, as we get into higher windows, maybe we would. But for now, I think this is fine. So this is going to, yeah, this is just going to help us to see plots in relation to each other. And so I've got this this statement up here, this overlay statement, and I'm going to utilize that down here. So I'm just going to say if overlay is false, then we're going to clear the image. All this is doing is resetting the image itself. So if I were to run 2 plots in a row, in fact, why don't I just do that? Let's plot the primes window twice. And let's go window low. Let's turn this back to 0 and keep window size at 10,000. And instead of, let's do window low plus 10,000. Oops. And we'll just do 10,000. And I'll just replace this in both places because I'm going to delete it in a second anyway. Okay. Although we should have a different primes list. I'm going to fudge this. I'm going to let this be the same length, and I'm just going to leave it as it is because we're going to write some loopage that's going to do a lot of work for us. So let's see how this plots. Appears to have not plotted. Interesting. Huh. Oh. Well, that might be why. Because I'm clearing the image before I'm showing it. Okay. Okay, so here's our first prime window. And I'm going to go ahead and delete this. If I close this, oh, interesting. It ran that as 2 separate operations. That was not the behavior I noticed before. Okay, well, my whole purpose of this overlay may have been for naught. We'll find out. Okay, so we've got this this plotting function, and I think it's done. I think it's doing everything we want it to do. So I'm going to get down into our procedural code for a bit, and I'm going to kind of rewrite a lot of this. So I'm going to go ahead and delete all of that. I'm going to delete this. And we're going to start off with probably the most important thing is actually the window size. Because you can imagine if we use a larger window size, you know, these numbers are going to settle a lot more. If we use a much smaller window size, we're going to see a lot more variation. And I'm going to bring back, let's see, I'm going to have a window start and a Windows, I'm going to call this Windows start and Windows stop. My reasoning being here is that we're going to get a lot of different windows, and let's get length 10,000 windows, and let's get 100 of them. So we're going to start at 0 and we're going to end at 100,000, but our window size is going to be 10,000. So by default, maybe I'll set the overlay to false because I'm not actually sure if it matters anymore, but we'll check it later. And I'm going to set zeros to false for now. And I'm going to just do a for loop. I'm going to say for I in range, and we're going to go from Windows start to Windows stop, and we're going to step by the window size, right? And window low is going to get I, right? And window high is just going to get window low, or sorry, it's not going to get window low. It could, but I'm just going to do a better practice here and reuse that variable name. So window high is going to get I plus window size. And then we're going to get a primes window based on these values. So primes window, this is going to be get primes in window. Get primes in window, yep. And even though I could nest a lot of these, I'm not going to. I want to have these pieces of data available because later we're going to dump them to a file. So we're going to go from window low to window high, and we're going to get a count of the primes in that prime window. This is dubious, actually, because the number of, if we, oh no, that should be fine. No, that's totally okay. All right. So let's get the window distances, and these are going to be, we're going to do that get distances function, and we're going to pass in the primes window, and we should be getting out a dictionary. And then we're going to, oh no, sorry, we're still getting out a list here. So this is a list of distances, this is a list of primes. So we've got the primes list, we've got the distances list, and we're going to now get the maximum distance, right? Because our plotting function needs this. And our data set, when we build it, is going to need this as well. So max prime distance is going to just get the max of the primes window distances. And now we're going to get the distances distribution, right? This is a lot of stuff that we're going to have sit in memory for a very small amount of time. And this is just calling out to that build primes distance distribution. And we pass into this the primes window distances. And this is where, if you remember, we had this include zeros. And we're going to, for now, well, this is going to be what we use. This is not going to be what we throw into our data. So this is what we're going to use for plotting. And I'm just going to set this to whatever we decide up here, right? So whether or not we're going to include the zeros, which right now we're saying is false. And so that's our distances distribution. And we can just use that to go ahead and plot the primes window for each of these. So distances distribution, we're going to go from window low to window high, right? That's what we've got up here. Window low gets I, window high gets I plus the window size. And we have this overlay. It's set to false right now, so I'm just going to say overlay is going to get the overlay, whatever that is. And I think that's it. Barring any errors, and I don't see any flags for errors over here, I think we can run this, and we should get a range of plots. Oh, there's an error right there. What is that? Window low, window high, overlay. It's overlay. Is that not the name of that function? Plot primes window. I'm just going to grab all of this. That's distances distribution, window low, window high. Oh, that's why. Because we've got a primes count. And we need to pass that in as well. And I think we called that number of primes, or num primes, if I'm not mistaken. Okay. Right? Num primes, yes. Okay. Let's see if something magical happens. Okay. One thing. Oh, okay. Right. So this is plotting one thing, and notice in our window over here that it's sort of paused after plotting this. Now, if I close this, then it's then it's going to error. Okay, so primes count. Let's find out what's going on here. Primes count is undefined. Huh. Maybe that needs to be, let's just do that. Okay. Okay, great. So this is working. And notice that this is going to, the prime window numbers are going to change. So now it's from 10 to 20,000, not inclusive. And as I do this, we can see that the shape stays fairly consistent in certain ways. And we're only going up to 100,000 here, but we could go up to 1 million. Now, I'm going to see if I change this overlay, what happens. Because this is something, behavior I encountered before that I actually thought was really cool. But let's just see. Okay, so here's our 0 to 10,000 and 10 to 20,000. Huh. I wonder what I'm doing differently here. One thing to notice here is that these numbers are switching around, right? These distances, the distances that are vying for first are kind of switching around. 2, 4, and 12, 2, 4, and 10. Yeah, I'm not really sure why that is. I actually think this should go down here. Oh, no, it shouldn't. Yeah, there's some inconsistency with what I did before and what I'm doing now. But that's okay. All it did before is it kind of overwrote itself, and so we'd get this sort of like colorful sludge that showed the progression of prime distributions across windows, and it's just kind of cool. But it is also very okay to not have that. So at this point, I've got these series of images that I can look at, but it would be nice to have like just a video clip. And to do that, I'm going to go ahead and write a stitching function. So the first thing that I'm going to want to do is save out some figures. And these I'm going to put in, I'm going to just use this save figure function or method that's tied to pyplot. And I'm going to save this out to a file called prime window. And then I'm going to stringify the window low, and I'm going to fill it with zeros. So this is just to make consistent file names that that if I sort those file names, they're going to be in an order that I can stitch them together exactly by their file name. So I'm just giving a lot of zeros leading up to the window size, and it just looks like that. If I was dealing with prime windows that were in number spaces where there were more than 10 zeros, then I'd have to do this a little differently. I'd have to maybe increase this number, or I would figure something out. But this is going to do for what we've got here. And I'm not going to show this anymore. Instead, I'm going to output some images. And I think if I do that, let's just go into, let's go there, exploring prime windows. I'm going to make two folders. I'm going to make an images folder, and I'm going to make a data folder. And we'll use the data folder soon. But for now, we're just going to use this images folder. And if everything's cool, I think we can just run this, and we should be able to see all these. We should be able to output files. So okay. And sure enough, we've got images. And notice that they're in order. So this file name is always going to be before this. And cool. Okay, this is what I was talking about. This is the effect where we get this sort of overwriting sludge, where each plot is going to overwrite another plot. And I think it's kind of cool. And we can kind of get this idea of a progression of the windows. Although I think what I'll do is strike out these annotations in this case. So let me just do that really quick. So we've got our annotations here, and I'll just say if, what did we call that? We called it overlay. If overlay is false, then we'll do the annotations. And yep, I think that's it. So I'm going to run that again, and we'll take a look at these images and kind of get a sense of, you know, what this looks like. It's sort of like taking a cumulative viewing approach, which I think can be informative. So let's, I guess I closed that window. Images, and let's look at the final one. So we can kind of see how these platforms are descending, and it's kind of stretching out to the right. And we'll see this much more clearly in a video. And let's go ahead and write that. So I'm a big fan of video, and I did a lot of work on thermal imaging, fusion, you know, data fusion for pedestrian detection, both with fusion neural networks and with data fusion as a pre-processing technique, where, you know, if you have a parallel image set of pedestrians and the thermal imaging, right, an RGB image and a thermal image, you can replace, arbitrarily replace a concept of luminosity called lightness, or, you know, the light factor. You can replace that with a thermal component. And so when you do that, you don't lose the morphological characteristics of the image, right? You maintain those, and you highlight things that have heat, and that's often humans, or, you know, neon signs, or car engines and things like that. It's kind of a nice technique, and yeah, it's just something I've done a lot of work on. And that's all from taking video, and then you can stitch that video back together, and you have it's almost like the way you imagine Predator, if you're familiar with Predator, sci-fi Predator seeing. You get some morphology in there, but you definitely get a lot of infrared in there, and it's pretty cool. So I'm going to write a function, and a lot of this I borrowed from let me just go ahead and sync my code really quick. And let's call this finish image output. And so those images should be up there. I'm going to be deleting them and doing a number of other things as we go, so they're probably not going to persist. But the way that this approach works is we'll be deleting and reconstituting those images pretty often. Cool. So I'm just going to call this stitch video, and I'm going to pass in a directory, which by default is just going to be that images directory, just to make it a little more convenient. And I'm going to give it a default file name of video.avi. And I'm borrowing that from the original, the person who originally wrote this code before I grabbed it and adapted it. In fact, I'm going to just pull up this Stack Overflow page. And this is true of really any coding you do. You're going to find so much on Stack Overflow. Google is your best friend. You know, it's great if you can code something from scratch, but you know, coding complex visualizations from scratch means that you had to, at some point, figure it all out yourself. And the documentation around a lot of this stuff is pretty poor. And if somebody else already figured it out for you, you know, then you've got a code base that you can work with, and it's super helpful. It's something that I would say you're going to end up writing better code if you can figure out how to find well-written code. And, you know, if you're doing something like this every day where you're stitching together a series of images, sure, you're going to get really good at that. You're going to author this off the fly. But if you're only using CV2, which is OpenCV, if you're only using this, you know, once every few months, there's kind of no way to remember this. So you could either have it stored somewhere, or you could just Google it. And I'm just recommending you get really good at searching for things. Cool. All right, so we're going to stitch together this video, and I'm going to delete the images that are in that directory, because I want to just be able to look in that directory at any time and take whatever's in there. And if there's already something in there, then I'm going to stitch those into a video, even if it's not relevant, right? Like, you know, like a picture of my cat or something, you know, it's like, oh, plot, cat picture. And that's not what I actually want to do. So that being said, I'm going to go ahead and delete all of these and come back over here. So stitching the video, we're going to say there's an image folder, and that's the directory. And there's a video name, and that's going to be the file name. So by default, this is video AVI, but I'm pretty big on naming things. So I'm going to give it hopefully a better name than that. The images are going to be the sorted images from the listing from the directory. So we're going to need another library for this. And I'm going to grab those right now. So we're using CV2. And we're using CV2 for the image manipulation to stitch into the video. And we're also using the OS library. And I'm pretty heavily considering doing, one of these streams on OS for file manipulation in your terminal. I use this all the time. And, there's kind of a steep learning curve for, say, Bash scripting, but there isn't for Python. And the OS and OS utils, there's a few modules, a few libraries for traversing your terminal with Python, and they're amazing. So this is going to get the sorted images out of our directory. So I'm going to just say, I'm going to do this in a comprehension. So image for image in a directory listing, list dir of the image folder. And that'll just get us all the images that are in there. And the only thing is, right now, this on a Mac, this is going to get an extra file that we don't want. That's going to cause it to crash later. So I'm going to use this string method ends with to see if it is a ping. And if it's PNG, then we'll add it to this sorted list of images. And because these have good file names, well, I deleted them all, but because they will have good file names, this should be the images in order. So the frames should go from each subsequent window, from each window to each next window. All right, so next we're going to get a frame, and we're going to use CV2 to just, if you've used MATLAB or skimage, this is a super common function across a lot of languages. ImRead, it's just image read. And we have to grab the path of the image, and we're going to concatenate the folder, right, with the actual image name. So this is going to be image folder, and we're going to just, for each of these, this is our initial frame, right? And let's see, we're going to, well, I think that's, yeah. Then we need a height and a width. And even though I'm calling out this layers, this is the depth of the image. So if you have something that's not sort of a pure grayscale, it'll be probably RGB, but we don't need this layers. So I'm gonna put an underscore there. We just need the height and the width in order to define the video itself, which we're going to do like this. So video is going to get CV2 dot video writer, and that's just the CV2 constructor that's going to build a video for us. And we're going to put in the video name, which is coming from up here, and we're just going to put in a couple of these parameters, including the width and the height. And now we can start patching things onto the video. And that's going to be just for image in images. So every one of these images, we're going to say path to the image, and we're going to say ospath.join. That's the image folder, image, and we're going to write to the video. This is sort of like appending to a list. We're going to use this imread again, and that's just the path to the image. So one thing to note here is that there's an assumption here that all these images are the same size, and they are, given the way that we made them, But if you were trying to stitch together a bunch of different sized images, this might not work. So I'm going to also remove each image. So that's just os.remove. So as soon as I write it onto the end of the video, I'm going to delete that image. And then at the end of this, I need to sort of clear out my CV2 instance, and I also need to set the video. So this is just releasing the video exactly as it sounds. So I think that's that function, and I think we can go ahead and make a video. So I'm going to change this from 100,000 to 500,000, and I'm going to set overlay to false for now, because I think what we want to see is sort of like the squirming pattern or something like that. We want to see how this pattern sort of adjusts itself as it moves through these windows of primes. And so, so we go through all this, and we've got all of these. Yeah, we've got everything we need here. So since we've got this stitch video function, I'm going to pass in the directory, which I don't, here, I'll just grab the, I have this tendency to overtype, and it turns out that copy and paste leads to less errors, as probably everyone watching this realizes. But I have a tendency to type when I should copy paste. So I could name this file name video.avi, but I want to make something a little more meaningful here. So I'm going to name this prime windows from, I'm going to go from the Windows start, and there we go. That's what's going on. Go from Windows start, and I use underscores a lot to separate parts of file names, and go to Windows stop, and I'm going to go by the window size, and I'm going to put whether or not the overlay is part of this, because that will change the video. Like maybe I want to show the video with the overlay and then without the overlay, and then I'm going to show whether or not I included the zeros. So I think, and then the file name, which I'm just exporting to AVI. I think I could change this. I could change the encoding to an MP4, but I think it's just AVI by default, and that's fine. So I think this will work. And let's find out. So notice we've got our ranges, and one thing to notice here, one thing to note here is if I change this overlay to true, the runtime, let's say the memory usage will be much higher. And so, you know, for that reason, I am not using the overlay here, because, well, the runtime is still pretty slow, interestingly. Wonder what's hanging it up. I guess we will find out. Yeah, I have a feeling this isn't running and that we are getting the overlay, but I can, this is almost this is almost done because we're only going up to 500,000. And we can take a look at what's happening here. Okay, all right. So if we look in here, there is a video called Prime Windows from 0 to 500,000 by 10,000. Oh, well, no, this is fine. Yeah, this is okay. This is an okay name. All right, so let's just open this. And this should open up in VLC. And we can watch the progression of this. And I think it's kind of cool because if you see this over time, these numbers will sort of drift down, like these numbers up here. They'll sort of drift down, and these numbers out here will sort of drift right. But there's a kind of randomness to it. And you know, the thing I was thinking about when I was playing around with this earlier is that we could look at the variance, or we could look at the standard deviation for these counts, and my suspicion, you know, and this is a sort of not very reality conspiratorial suspicion, is that if we increase this window size, we're going to see a lower variance, right? And in general, the larger distances are going to have higher variance, and the lower distances are going to have lower variance. And then, you know, 6 is going to have the lowest variance. I mean, what we're seeing is just across all these numbers, 6 is kind of the number, right? So let me go ahead and sync this. Video stitching. And hopefully that video isn't too large for GitHub. That's something that I mess up sometimes. Let's just take a look. Oh, it's only 23 megs. That should be fine. Okay. So the last thing we're going to do here, now that we have kind of a look into this shape of primes, is, you know what I'm going to do here? I'm going to set the overlay to true. I'm going to start this running, and hopefully we can get a video out of it that has the overlay to kind of get a look at it. I think it's cool. And while that's happening, I'm going to code some stuff out. So we're going to make a CSV. We're going to make a data set. And more than that, we're going to make a process for making data sets for these windows. And I made a list of what I think is important. And I'm just going to call this the data fields list. I think the window start, right? That's important. The window stop. The window size. The count of the primes, right? The prime count, primes count. Let's call it primes count. I'll call it prime count. This is such a non-issue. I don't know why I'm hung up on it. Okay, so the maximum prime distance, right? These are all sort of easy characteristics of a prime window that we can just grab from what we already have. The primes list itself, right? And then something that I'm going to call prime distances tuples, but this is really just a transformation of the dictionary that includes zeros, the dictionary of distances that include zeros. And the reason why that's the one that I think we should include is that it gives us the opportunity to make vector comparisons using cosine similarity, or by using a max length, you know? So like if one vector is longer than the other vector, we could just trim off the longer vector, and we could do Euclidean distance. But the distances should be in order to compare them. And that's actually why we want to include zeros here. And we'll get a look of what that is in the data once it's oh no. Something crashed over here. Oh, no it didn't. It's because I didn't actually run this the way that I meant to. Nope, that's not it. Let me just get this running, because I think it's going to get bogged down. Okay. All right. So let's name this file. And this is, if you remember, I made this data directory over here under, where is it? Exploring. There it is. I made this data directory. So that's what we're going to use to write out our CSV file. And I'm going to say file to write. And this is just going to be the name of it. It's going to be in data, prime windows from, and this is going to be a lot like the video name that we gave, from the Windows start to Windows stop. It should really be Windows stop -1, but I'm just going to leave it. Windows stop by window size. So Windows start, Windows stop, Windows size. Start, stop, size. Yep. And I could call this a text file, but I'm going to make it a CSV. And you can generate it this way, and then if you wanted to, you could look at it in Excel, or you could open it up in Pandas, or do any number of things with it. So so we've got all of this for loop, right? This massive kind of for loop that's going on where everything's happening. And we're capturing a lot of data in here. So I just want to use it as we capture it. And this isn't really, in general, you should go for a separation of concerns in programming, but I'm not going to do that here. I could, but if I was going to really do a separation of concerns, probably what I would do is create a prime Windows class instead of having all these separate functions, because we could have a single class that is a prime window and have a bunch of class fields, and then it would be easy enough to just append to a data set that that class and the metrics on that class. So I'm going to say with open, and this is just this is for file reading. So with open, I've got the file to write, and this doesn't exist yet, but it's going to go ahead and create it. And I'm going to assume that we want to overwrite the file if it's already there. Because we have these different names, like anytime, like all of this should stay the same. There's no randomness in this. So if I change any of these, it should make a different file. And, the overlay and the zeros don't matter. It's just the Windows size, Windows start, Windows start, Windows stop, and Windows size. So this should be fine. With open file to write as F. And all of this is going to sit inside of this with open concept or construct. So once with open finishes, it's going to automatically close this file. And there are other ways to write to files in Python, but this is one of the most suggested ways. If I was doing this with other libraries, I would probably use pandas, or I would use some other 2CSV with pandas, or I would use the CSV module for Python. But this is, I actually find this easier than the CSV module personally, but not as easy as pandas for doing a similar thing. So I'm going to write these fields, these data fields, to the file, and that's going to be our first line. And notice that they are separated by a comma with no spaces. So this is going to give us that comma separated values. And I'm joining the data fields. And then at the end of that line, I need a new line. When you write lines to a file like this, you need to, you basically just need to make a new line explicitly, like so. So let's look. So that's writing the initial thing, and that's only going to write once, right? Because then we're in this for loop, and once the for loop ends, then we get on to stitching the video together. And the video finished over here, and we'll look at it in a little bit. So let's see. I'm going to need, notice we've got this distances distribution, and we can't say for sure that this is going to have the zeros in it or not, and we do need the zeros. So I'm going to make something, I'm going to basically copy this, and I'm going to make something just for data storage. So I'm going to say for just for storing for the data file, and this is going to be the sorted version of all of this dot items. Okay, is that it? Oh, and we need to set include zeros to true in order to represent this in a consistent way in the stored data set. So So this is essentially the same thing as this, but we're not getting a dictionary out of it. We're getting a list of tuples or a dict items object, I think is technically what that is, but it's essentially a list of tuples. Like we could cast this to a list and it would be a list of tuples. But currently it's in a form where we can write it to the file where it'll be readable in a way that makes sense. And we'll see that very shortly in the file itself. Okay, so we've got this. And then the last thing we're going to do in this loop is we're just going to use the write method, and we're going to write lines. And we're going to separate them. So let's see what we wanted to write. We wanted to write all of these fields. So I'm going to take this, I'm going to set it over here, and I'm going to grab all of this. I think the names are different. That's okay. We'll figure that out. So there's 1, 2, 3, 4, 5, 6, 7 of these, 7 items. And notice I don't want to put spaces. So that's 4, 5, 6, 7. And window start, window stop. And I think what these are named in this for loop is window low and I think window high. Yeah, window low, window high. And in this case, we actually want to do the -1. So I haven't been doing this. I haven't been, because it's 0 to 9,999 actually inclusive. But because we're storing this in data, we don't want to include that upper bound. I think there is an instance where, let's say you have a window that happens to end on a prime number. We're not doing that because we're going by 10,000. But if that did happen, you wouldn't want to include this erroneously. You wouldn't want to include the upper bound erroneously. And this should actually be window high, not window low. Okay. And then window size should be the same. Window size. And then prime count. So that's num primes. And then max prime distance is here. So max prime distance, grab that, and primes list. So we've actually just got the primes list in the form of the primes window. And that's just going to be a list of primes. And it should be in the order that it's encountered. So that's helpful. on the other end of the data, right, if somebody reads in the data and it's out of order, the primes are out of order, it's not a big deal, they can sort them. But this is kind of a nice thing. And then we have the distances. Oh, I definitely don't want to name this the same thing. Distances, I'm just going to name it what it is, distances for storage. And I'm going to throw that in here. And I'm going to make a new line. And I think that's it. I think that's all we really need to do there, barring I have some error. So let's look at that, and then let's look at this other video really quick. And then I'm just going to say some stuff about, you know, critical thought and creativity and blah, blah, blah. And then we'll call it a day. So let's look at, I'm just going to open this up in VS Code. So we've got this data directory here. Oh, you know what? Let me sync this. Git adder, finish data write, and oh, there's nothing in the data file because I did not write this file or write this data. So let's do that first. And I'm going to comment out this stitching because I don't want it to take up too much time. All right. Then we waited. So, you know, a big part of my reasoning for doing something like this, it's not just because I think this is kind of fascinating, these patterns. I do. And it's nice to be able to wonder about something and explore it and get to a point where you realize that there's so much more to explore, right? There's a lot going on in these primes. That's really enjoyable to be able to do that. Part of why I'm doing this is so that people can maybe get the idea that if they're thinking about something and they don't know how to solve it, or sorry, and they're not familiar with it, you know, you can go read about something, right? But you can also explore it prior to reading. You can read about it, then explore it. But if you're going into, you know, data science spaces, if you're going into machine learning, there's a lot of exploration, and it's a creative process as much as it is a process of, say, of learning about, you know, learning about things. So yeah, I just want to, you know, show that this is kind of like, this seems like a hobby approach right here, but I'm making a data set that is valid, and somebody could grab this data set and do anything with it. I could go through it and start figuring out some statistics. I could do, you know, comparisons of the distributions in terms of Kullback-Leibler divergence, or I could compare them in terms of cosine similarity. And there might be, there are approaches there that, you know, undoubtedly somebody has done a lot of this, but I don't actually know that somebody's done a lot of that. I just realized I am plotting everything here. And so let me just set this overlay to false so that this goes a bit faster. Yeah, because it's set to true. So I was still plotting and generating the images, and that was not my intent. So this should go way faster. Yeah. Yeah, but, you know, for example, for next time, I'm thinking of scraping. There's this this site that has a lot of open, and I was thinking about scraping maybe all of it. I think I could scrape all of it, and doing, you know, making a simple recommender system, or just even comparing the books to each other, right? You know, looking at things like text cleaning and encoding of the books themselves, because if they're in the wrong encoding, I'm not going to be able to compare them, right? So doing processing on the text encodings themselves. It's something that, you know, it's something I've done quite a bit, but it's something that I think a lot of people wouldn't know that they could do, and that it's not that hard to do. You know, even a lot of this seems challenging, but it's not. And maybe for some of you this doesn't seem challenging. This is just, you know, building off of simple ideas. I mean, we just started off with an isPrime function, and we moved through this in a way where we got some distances, and then we thought about what those distances mean. And then, you know, at the end of the day, we're like, you know, we've got some working video and you know, an idea, and we've got a data set, and we've got another idea of what primes are. So all that said, let's actually look at this data set. Long story short, I'm trying to encourage people to be creative, right? To think of a problem and try to approach that problem in a way to understand it. So here's our CSV, and each line of this CSV has a couple things in here that are kind of interesting, right? Like we've got these lists, and then we've got these lists of tuples. The lists of tuples are just the, you know, the counts of the distances. So, you know, there's only one anywhere in this data set, and that's in the 0 to 10,000 block for what we're doing. And it can only be one, right? That's just the distance between 2 and 3. And then there's 205 2s, 0 3s, 202 4s, 0 5s, etc. And this is a pretty comprehensive data set. One thing to note here, you know, because this is comma separated values, the commas in the lists are going to need some kind of special processing in order to read them in effectively. If you use pandas to read this in, it's probably going to be fine. I don't know that offhand. I think it will, though. And it'll just load as an object that is a list, something like a list. And same goes for these tuples. So, you know, that's something to be careful with comma separated values, that you need to do some special processing around something that's a collection type, like a list or a list of tuples. So there's that. And let me go ahead and sync this up. And the last thing is just kind of looking at this, let's see, overlay false. And this is the, I want to say this is the overlay true. Yep. So let's see how that turned out with the overlay. Yeah, there it is. And so we can kind of see this kind of, it's sort of like an accretion, and the whole thing is traveling down, right? On the left side, it's traveling down, and on the right side, it's sort of traveling out. But it's not like, it's not consistent. And, you know, you could do this for windows of 100,000, or you could do it for windows of 100, and you're going to get much different results. Either way, I think this is, I think it's pretty neat. And yeah, please feel free to grab the code that I wrote, fork the repo. I might add things here and there to it if I explore this further, but as a template for, you know, kind of thinking about problems, I think this is okay. You know, as a template for synthesizing data, I think it's pretty good. So yeah, I'm going to see if anybody's been asking questions. And awesome. I'm going to spin this down, and it'll probably be live, or sorry, it'll probably be posted in a couple hours after it processes a bit. And yeah, I hope you guys have enjoyed it. I really like these kinds of problems, so, you know, I mess around with them from time to time, and I'm happy to share them. Next time, I might do some like terminal scripting with Python. I think that's one of those things that when you start realizing how easy it is to do terminal scripting with Python, it's great. It's so helpful. I might do that, or there's some other like generative network stuff that I've mentioned in the past. I think, hopefully in about a month or so, I'll have a set of topics kind of planned out so that I'm not just deciding in the couple days after I stream what I'm going to stream next time. But for now, we'll play it by ear. And if you have any recommendations or things that you'd like to see, post in the comments, send me a message through some venue. If you're at Galvanize, send me a message on Slack. And yeah, I think that's it. Thanks so much, and have a great night, y'all.